You know that feeling when you're in a car taking a sharp turn and you feel pushed to the side? Or have you ever looked up and wondered, how in the world does a satellite stay in orbit? Well, the answers to all of that, they're found in the fundamental physics of motion. And that is exactly what we're going to break down right now. See, it all comes down to this really elegant and powerful set of rules. We're about to unpack the language and the laws that govern, well, everything that moves, from giant planets all the way down to us. This is, the foundation of physics. All right, so here's our game plan. We're going to start with the absolute basics, get our terms straight. Then we'll dive right into the three most important laws in classical mechanics. You've probably heard of them. From there, we'll see how all this stuff applies to spinning, turning, and balancing. And by the end of this, I promise, you're going to have a whole new toolkit for seeing the physics that's happening all around you. Okay, so first things first, what are we really talking about when we say motion? Let's get our basic definitions locked in. So this whole field we're diving into, it's called mechanics. And yeah, it's pretty much the OG branch of physics. It's all about figuring out the fundamental rules of how and, more importantly, why things move. And right at the heart of mechanics is this one crucial distinction. An object is in motion when its position changes over time compared to its surroundings. But if its position doesn't change compared to its surroundings, well, it's at rest. Now, that sounds super simple, right? But that little phrase, relative to its surroundings, that is the key to everything. Okay, so now we know what motion is. But if we're going to talk about it like physicists, we need a proper language to describe it. And that language really starts with two key ideas. First up, we've got something called a scalar quantity. Now, a scalar just tells you how much of something there is. That's it. So when you say your speed is 50 kilometers per hour, or that a bag of sugar has a mass of 2 kilograms, you're using scalars. It's just a number, a magnitude. Nice and simple. But then we have our second concept, the vector. And this is where things get way more interesting. A vector tells you how much and which way. So it's not just 50 kilometers per hour, it's 50 kilometers per hour north. It's not just accelerating, it's accelerating downward. That little bit of info, the direction, is absolutely crucial. So let's just lay it all out. Scalars, they're simple. Just magnitude. One-dimensional. But vectors, they've got magnitude, times, and direction. They can work in 1D, 2D, even 3D, which means they need their own special kind of math to handle all that extra info. And this whole scalar vector thing becomes crystal clear when you compare distance and displacement. Distance is a scalar. It's the total ground you covered, right? Every twist and turn. But displacement, that's a vector. It's just the straight line from where you started to where you ended. And trust me, these two can be wildly different. Think about it like this. A bus travels 150 kilometers away from its station, and then it turns right around and drives 150 kilometers back. Okay, so what's the total distance it traveled? Easy, right? 300 kilometers. But what's its displacement? Well, since it ended up exactly where it started, its displacement is 0, a big fat 0. See how that works? All right, so we've got the language down, scalars and vectors. Now it's time to learn the grammar. We're talking about the fundamental rules of the game, the laws that govern all motion, and they were laid out centuries ago by none other than Sir Isaac Newton. And guess what? They're just as true today. Okay, here they are, the big three. First, you've got the law of inertia. Basically, things like to keep doing what they're already doing. If it's still, it wants to stay still. And if it's moving, it wants to keep moving. Simple. Second, we have the famous one. Force, mass, and acceleration are all linked. The more force you use, the faster something accelerates, but its mass can slow that down. And third, for every single action, there is an equal and opposite reaction. These three laws, they are the absolute bedrock of mechanics. So we've got the laws. Now let's put them to the test in a situation that's a little more complex than just a straight line. What happens when something starts moving in a circle? Well, to make something turn, you need a special kind of force. It's called centripetal force. And that name literally means center-seeking. It's this constant force that's always pulling the object back toward the center of the curve, keeping it from just flying away. And here's the cool part where it all connects. Why would that object fly off in a straight line in the first place? Think about it. It's Newton's first law, the law of inertia. The object wants to go straight. The centripetal force is that unbalanced force from the law that's constantly fighting inertia, pulling it and forcing it into a curve. See? It all fits together perfectly.
Motion isn't always just about getting from point A to point B. It's also about twisting, turning, and rotating. And sometimes it's about not moving at all. So let's talk about torque, and let's talk about balance.
So, if a regular force causes things to move in a straight line, what causes them to rotate? The answer is something called torque. You can just think of it as a turning or twisting force. Every time you open a door, you're not just pushing it, you're applying a torque around the hinges that makes it swing. Okay, now for a really important question. What do you think happens when all the forces and all the torques are perfectly balanced? When every single push, pull, and twist completely cancels each other out?
What you get is a state called equilibrium. It's the state of perfect balance. And here's a key point. Equilibrium doesn't always mean something is perfectly still. It could be moving, but at a constant speed in a constant direction. The main thing is that its state of motion isn't changing. It's totally stable.
But get this, not all equilibrium is the same. There are actually 3 types. You've got stable equilibrium. Think of a ball sitting inside a bowl. You nudge it, it just rolls back to the bottom. Then there's unstable equilibrium. That's like a ball balanced perfectly on top of a hill. The slightest touch and it's gone. And finally, you have neutral equilibrium. Imagine a ball on a perfectly flat floor. You can push it, and it just rolls to a new spot and stays there, perfectly happy. And just like that, there you have it. In just a couple of minutes, we've put together a really powerful toolkit for understanding the world of motion. So let's take a quick look at what's in your new physics toolkit. So what's the big takeaway here? Well, you now have the language and the rules. You can totally explain the difference between a scalar and a vector, between distance and displacement. You can talk about Newton's 3 laws like a pro. You get the physics behind what keeps planets orbiting and what keeps a skyscraper from falling over. Seriously, you can now officially start looking at the world around you and see it like a physicist. But I want to leave you with one final thought. Newton's laws? They are incredibly accurate for describing our everyday world. But what about the really, really weird world of tiny subatomic particles? Or the strange physics that happens when things move close to the speed of light? Do these same rules still work? Well, that's a mind-bending question for another time. Thanks for diving in with us.